Okay, let's get started. We're finishing up AvlTrees today. Before I do that, just wanted to make a couple quick announcements, which I'll do as well on Tuesday, which is, first of all, remember that we have, there we go, that next Wednesday, April 22nd, is the coding part of your final exam. So in lab, using Code Assessor, and you'll have a one-page cheat sheet for that. And you'll have 3 problems. I'll try to get a practice problem up by this evening so that you can play with one. And then the paper portion will be at the regularly scheduled final exam time. So these will be worth a total of 50 points, and the paper version will be worth a total of 70 points. So paper version at regularly scheduled exam time. No coding. And worth 70 points. So again, it'll be out of 120 points, but you have 120 points total. And finally, SAIS, if you fill out your SIS and hand in the confirmation form next Wednesday in lab, it'll be worth an extra 30 points. Okay, I do not want email on it. It's too much to deal with. Okay, there's just too many. It's a high enrollment course. It's just problematic. So hand in the confirmation form in lab next Wednesday, April 22nd, and worth 30 extra credit points. Lab points. Okay, so questions about that? Okay. Yes, hard one. Pardon? We'll have to look it up. It's in the, if you'll go to the academic calendar, it's there. I think it's the 30th. Okay, so Doug thinks it's the 30th. For sure, it's going to be from 8 o'clock to 10 o'clock. Okay? So that would put it on a Thursday. Seems reasonable. But I will get that up. Other questions? Okay. So today we're going to finish up, like I said, AvlTrees, and then we're going to move on into BTrees, which are another type of balanced tree structure, although they're not binary search trees. And if you'll remember, I kind of gave you a quick introduction to deletion last time, which is that you start it just the way you do with a binary search tree. So you have the 3 cases where it's a leaf, or it has 1 child, or it has 2 children, and you perform the deletion in the exact same manner as you do with a binary search tree. And then after you perform the deletion, you check to see whether it's still a balanced AVL tree, and if it's not, then you need to perform some rebalancing operations. And there's essentially 3 different things that can happen when you delete a node. So first of all, it may be that the height of the parent gets decremented by 1, and that happens if you were the only child of the parent. So case 1, its height is decremented by 1. occurs when you are the only child. So right here, if I were to delete Boo, that would delete Callista's height by 1. Okay, second case is that the height doesn't change, but it stays balanced. Okay, so if you were to delete Fred here, you have 2 children, but I'm sorry, you have, yes, Luther, the parent, has 2 children. So when you delete Fred, it doesn't change the height of Fred. And therefore, that's the real nice case, because if the height of the parent doesn't change, then by definition, we still have a balanced AVL tree, because the tree was balanced in an AVL tree before the deletion. Since the parent's height didn't change, we must still have a balanced AVL tree. So that's kind of the Goldilocks situation. And then we have the situation where the height doesn't change, but it becomes imbalanced. Okay? So if we delete D'Antonio here, then even though the height of the parent, Eunice, does not change, it becomes imbalanced, because with no child, the height of its left subtree becomes -1. The height of its right subtree is 1. Therefore, it's imbalanced, and we're going to have to rebalance it. Okay? And both cases 1 and 3 can lead to a situation where you may have to do some rebalancing. So as an example, let's say that over here we had beforehand aardvark. Can't spell aardvark. I think that's how we spell aardvark. Well, we're close. There's a missing D. At any rate, if it had been like this would have been a 0. This would have been a 1. Okay? This would have been a 2. This would have been a 3. And this would have been a 4. And can anyone tell me, is that still an AVL tree? It is. Yes, because if you look at any pair of children, you'll notice that there's still, at most, a difference of, actually it's not, right here. So, in fact, baby Daisy is unbalanced. So, let's, I have to fix that. I was kind of hoping that was going to imbalance it, so I'm going to have to find a different example. Just a moment. It's probably going to have to be actually, that was the right example. I just delete, if I delete Boo, okay, now that's still going to leave Callista's height at just 0, so that's not going to be imbalanced. I want to try to imbalance this puppy if I can. I think I know how to do it. Boy, it's going to be hard to squeeze something in here between baby Daisy and Binky. Bark. Okay. And now I believe I can add aardvark here. 0, 1, 0. Yes. 3, 4, and Yes, that is still a... So what I have there is in fact a AVL tree. And now if I have situation 1 where I delete Boo, okay, Callista's height becomes 0, and that causes now an imbalance right here for Binky. So in fact, case 1 and case 3 can both lead to an imbalance situation. Now, Dr. Planck's notes kind of go through a analysis of each of these situations, but you really don't need to go through that full-blown analysis of the situation. Instead, you can just kind of go to the more general case, which is what you're going to do with your rebalance routine in the lab. So the general idea, after you delete, we'll do it with a concrete example now. We'll use some numbers. Okay, so we'll have 5 and 15, and we will have here 20. Okay, so this is a balanced AVL tree right now. Okay, if we do the numbering 0, 1, 0, 2, everything's fine. If we delete 5, you can see that we imbalance it. And as I told you last time, when you do a deletion, the imbalance is going to now occur on the other side of the tree because you're shortening your side of the tree. Thus, it's the other side of the tree that is going to be potentially higher and needing to be rebalanced. Okay, that's different from an insert. When you insert, okay, so changing it, if we insert it like here, then the imbalance is going to occur on the side of the tree where you did the insert because it's going to increase the height of that side. So kind of delete and insert causes imbalances on different sides of the tree. Okay, so we're doing but instead we're doing this delete right here. So what we're going to do is we're just going to check the parent. And like in the insert case, we're going to have to potentially iterate our way up through all the parents to the root, at each point checking to see if there's an imbalance. Okay? So an imbalance could occur, and now I'm going to go to the more general case. So what's going to happen if an imbalance occurs, let's say that the delete occurred in the left subtree. So there was a delete over here. Okay, so what's going to happen if there's an imbalance, it's going to mean that this one has a height, say, of h plus 2, and this one has only a height of h. So there's going to be a difference of 2 with the right subtree having the greater height. Okay? So when we detect the imbalance, what we do is we figure out which tree has the greater height. In fact, we're agnostic. We don't care whether the delete occurred in the left or right subtree. We simply look and see which of our true trees has the greater height, which in this case is the right subtree. Okay? So now the right subtree, we can take a look at that, can actually be shown as its own two subtrees. Okay, and there's two cases. Okay, the first case is that the left subtree has the greater height. Okay, so if there's an imbalance, then there's actually three cases that are going to come up, which is that the left and right subtree have the same height, Okay, left subtree height is 1 greater than right subtree. And right subtree is 1 greater than left subtree. Okay, so we're talking about these two subtrees right here, L and R, for these three cases. Okay, so let's do 2 and 3 first. So if the left subtree's height is 1 greater than the right subtree, we have our zigzag case. Okay, so with our rebalancing, we're going to have to perform a rebalance. And does anyone remember how we handled the zigzag case? If I label these nodes K1, K2, and K3, what are we going to do in order to rebalance the tree?
Double rotation.
Double rotation. About which node?
K3.
About K3, about the grandchild. So when we have a zigzag rotation, we find the grandchild of the parent and we do the double rotation about the grandchild. So in this case, we would do a double rotation about K3. So that's handling case 2 right here. Okay, in this case we assume the left subtree's height is 1 greater than the right subtree. So we have the zigzag situation, and that's how we rebalance with a double rotation about K3. Okay, questions about that? Okay, so in fact I'll write it here. Case 2 is the zigzag case. Okay, so double rotate about grandchild. Of imbalanced node. So here that is K3. Okay, so that was case 2. Case 3, we're going to assume that the right subtree has the greater height. So the imbalance is like that. Okay, that's a zig-zig situation. We'll call this K4. So if it's a zig-zig, how do we rebalance? Doug?
Rotate about K2 once.
Rotate about K2 once. Very good. So case 3 is a zig-zig, and we do a single rotation about the child of imbalanced node. So that is K2. Now, in your notes, if you come back and look at this in 2 weeks, if you look at this, I just realized you might think that K3 and K2 refer to the imbalanced node. The imbalanced node is K1. So you might just want to note in your notes that the imbalanced node here is actually K1. What I'm talking about here is the grandchild and the child. So when I say K3, that's the grandchild. The imbalanced node is actually K1. Okay, so maybe a better way, a clearer way of writing that might have been, say, K3. So I might have said rotate about the grandchild K3 of the imbalanced node K1. zig-zig, maybe it would have been better if I'd said about the child K2 of the imbalanced node, which is K1. Maybe that would have been a little clearer. I'm just trying to make sure that in 2 weeks when you come back, you don't get confused. Okay? So we haven't handled the first case where the left and right subtrees have the same height. So let's just take a look at what that could mean concretely. Okay, so coming back here, we had 10, 5, we had, let's make this 20, 15, and 25. Okay? So we delete 5, leaving us with this tree right here. Okay, so if we look at the heights, okay, we see that we have our imbalance here. So we go and look, we see that the right subtree has the greater height, so we go and take a look at it. And now we look at which of its two subtrees has the greater height, and which of its two subtrees has the greater height? Neither. They're equal, right? So this is the case we're talking about. Okay, so we have to figure out here whether a zig-zag case works or whether a zigzag case works. Okay, so let's just do it concretely first. Let's do first the zig-zag because it's the easier one. Okay, so if we do that, actually take a moment and do it. This is always good exercise. So take a moment, do a zig-zag, do the rebalancing, assume it's a zig-zag situation. Okay, so do it assuming this situation right here. Okay. So I'm just going to show you. So what happens is the 10 rotates down. Okay, 25 still is a right child of 20. And what happens to 15? Becomes the right child of 10. Okay, is this an AVL tree? Yes. Okay, so that looks pretty good. So it's kind of tentatively looking like a zig-zag rotation would work. Okay, try doing it with a zigzag rotation now. So assume it's this way. So do a zigzag rotation. Okay, again, I'm going to just show you. So first of all, it's a double rotation about which node? 15. So the first rotation is going to produce 10 goes to 15, and then we have 20 and 25 coming down like that. So we rotate 20 down. It's really in balance now, but we still have to perform the second rotation. And is that an AVL tree? Yes. It looks like either one works. Looks like either a zigzag or a zigzag works. And that, in fact, is the case. Turns out that if the two subtrees that I showed you here, L and R, if they're the same height, you can do either rotation, and therefore I suggest doing a zig-zig because it's easier, more efficient. Okay, so case 1, either the zig-zig or zigzag solution works. So use the simpler zig-zig solution. Okay, now I don't want you to get into what Dr. Planck likes to call proof by Cosmo, which is, so Dr. Planck has a big thing against Cosmopolitan magazine. He thinks it's always trying to show things in their worst possible light so that women would buy products from them. So he calls it proof by Cosmo, where you just take 1 or 2 examples and say, because it works on my 1 or 2 examples, it must be true. So that's why you sometimes see his proof by Cosmo statement in there. At any rate, we shouldn't just assume that this works because it went on 1. I'll show you why it works for the zig-zig case. I won't bother with the zigzag case. So you can do that as an exercise if you wish. So let's say that, again, we have the situation where the right subtree is, let's just do it, the right subtree is here and here. We're going to assume that the heights, let's give them at least specific heights. It'll make it easier to think about. So let's just say arbitrarily this height is 5, that this height is 4, this height is 2, and we're assuming these have the same height. So I find at least it helps to work with specific heights rather than trying to be abstract. So here's at least a concrete example, and the imbalance obviously is at the root of this subtree. Okay, so I'm claiming that a zig-zig rotation is going to solve the problem. Okay, so here's K1, here's K2, and we'll just call this A. Okay, so I claim that the zig-zig solution is going to work. That means K2 is going to rotate up, K1 is going to rotate down, A is going to be down here. We're going to have now R over here, and K1 is going to end up adopting L. Right? Do we agree with that? That's our rotation about K2. Everyone in agreement? Okay, so let's just recompute the heights. Okay, so the heights of A, L, and R don't change. They're still the same. So we still have 2, 3, and 3. Right? So that means the height of K1 is what? 4. And the height of K2 is 5. But importantly, we see that if we look at the difference in heights between A and L, they're 1. The difference in height between K1 and the height of R is 1. Therefore, that is an ABL tree. Okay. Now, I know I use specific heights here, but this is much less a proof by Cosmo. Okay. You could certainly replace the 2, 3, 3, 4, and 5 with some variables like, I could certainly have said, well, if this is H, this must be H plus 2, and this must be H plus 3, and you could easily see that you could work it through and see the same thing goes for any value of H. Okay, so that's my proof for the zig-zig case, and I'm not going to bother with the zigzag. It's the same thing. If you do the movements and you calculate the heights again, you'll find that it's an AVL tree. Okay, so questions about any of this? Okay, now, when you're done with the rebalancing, it's not like an insert. You still may have some imbalance. Okay, so just because the first one, just because you manage, so when you do a delete, it imbalances, so we do a delete. Okay, we're way down here somewhere, and it imbalances it, and here you have something that's much, much bigger. It turns out that when you delete over here and do your rebalancing, it may further shrink things up here so that this thing is smaller than something over here, and you have to do multiple rebalancing. In fact, Dr. Planck has an example at the very end where you delete Xerxes from this tree. So go ahead and do that right now, and you're going to find that you actually need to do 2 different rebalancings. So take a moment, try to rebalance this tree after you delete Xerxes from it. So start, of course, by the situation where I'll start you off on the right track. If you delete Xerxes, the first imbalance is going to be right here at Xavier. See if you can figure out why, do that rebalancing, and then see if you can figure out why that's not sufficient to rebalance the entire tree. Okay, can someone from the back of the room, not going to take it from the front of the room, someone from the back of the room tell me what this subtree looks like after I delete Xerxes? How do I rebalance it? Okay, so rotate about, how do you pronounce it? Gala. I'm going to have trouble. Gala. Why he has to choose these names for me? Okay, so why the rotation about Gala, Samantha? Okay, so you're right. The imbalance is about Xavier. So what kind of rotation do we have? I'm sorry. What kind of imbalance do we have? Is it zigzag or zigzag? That may be true, but I'm going to let Samantha. I'm not trying to put you on the spot, Samantha. I'm just trying to see, I'm trying to figure out what your reasoning process is, okay? It's okay, yeah. You can confer. Okay, so let's do it. Let's actually do a rotation about Gala and see what happens, okay? So if we do the rotation about Gala, then Xavier comes down here. Okay? And who adopts Thor as, so Thor becomes Xavier's, so it's still not balanced, right? So we actually have this zigzag situation. So look at Xavier and the heights of the two trees. This is now 1 and this is -1. So the left subtree is greater, so go and look at it, and then look at its two children, and the greater subtree is the right subtree, so it's a zigzag. Okay? So we actually do the rotation about Thor here, a double rotation. Okay? This is good though. Is walking through, does this make sense to everyone? Because I didn't get an overwhelming response there from the back of the room. I want to give Samantha her props from stepping to the plate and responding. Okay? Is that clear? Okay, because this is guaranteed to be a test question, right, on the paper portion. So it is going to be, we're double rotating about Thor. So the first rotation is going to bring Gala down, and the second rotation is going to make Xavier a right. So we're going to end up with this, Galos, and yeah, I know, you all get to laugh because I have trouble with these. Okay, so this is my new tree. Okay, so if I do my heights, okay, what do I notice about Daisy? After I rebalance Thor, these are my new heights, 0, 0, and 1. What do I notice about Daisy? What are her two children? They're imbalanced. Binky is a 3, Thor is a 1. So even though I rebalanced about Thor, in the insert case I would be done at this point, but it's not. I'm not done here in the delete case. In the delete case, I'm still going to have to do some kind of rebalancing with Daisy. Okay, so take a moment and figure out what that rotation is that's going to solve Daisy's dilemma. How are we going to rebalance Daisy? Okay. So I'm going to let this powwow over here. What did you come up with?
So I said if you look at Daisy's two children, Binky's greater.
Mm-hmm.
And then,
Very good.
Baby Daisy's greater than Calista. So
Very
it's
good.
The zig-zag.
Very
So
good.
rotate about Binky
Very good.
once, and then it would be balanced.
That's right. Very good. So you look at the two subtrees for Daisy. The left subtree is the greater height, which is Binky. Now we look at Binky's two subtrees, and we see that the subtree rooted at baby Daisy is greater than the subtree rooted at Calista. Therefore, what we have is a zig-zig situation, and we rebalance by rotating about, in that case, the child of Daisy, which is Binky. So we're going to rotate about Binky, which means that Daisy's going to come down and become a right child. So Daisy's going to hold on to Thor as her right subtree. She's going to adopt Binky's right subtree as her new left subtree. So if we take all of that into account, so the 3 steps, so Daisy, I'm going to write them down so that you can see what happens. Daisy becomes Binky's right child, and Daisy adopts Callista as her new left subtree. Okay, so those are the 2 changes that are going to take place. I'm doing that here because I'm going to have to now move my browser, and that's going to cause some issues. So let's delete this, delete this. You're going to see the solution. So this is the solution, and you can see Daisy did in fact become Binky's right child, and you can see that Daisy adopted Callista as her left subtree. And down here you can see that Thor is in fact the root of the subtree for Gallos and Xavier. So that required 2 rebalancings. So basically, with delete, the idea is that, so with delete, you first delete as you would in a binary search tree. 2, you iteratively check the parent nodes, or check the parent node. Okay? And if the parent node is now imbalanced, you rebalance. Or rebalance the parent's tree. Okay? If after rebalance, or if after rebalancing, the parent's height hasn't changed, you're done. So you can break out of the loop. Okay, the reason for that is if after rebalancing the parent's height hasn't changed, well, we know that in the original tree, it was with the parent at this height, it was a legitimate AVL tree. Therefore, it must still be a legitimate AVL tree if the parent's height hasn't changed. But if after rebalancing the parent's height changed, you'll have to repeat the check by going to that parent's parent node. And keep doing that until you reach the root. Okay, so the other reason you're done is you reach the root and you can't go any further. So this is, in essence, right here, what check balance and rebalance are doing in your lab. And you can call check balance and rebalance for both your insert and delete. You don't have to know whether it was an insert or whether it was a delete operation. So don't fall into the trap in your lab 11 of thinking, or lab B. Does anyone know why it's called lab B? Yes. Hexadecimal. Very good. So there you have it. So it doesn't matter whether you do an insert or delete. You just call check balance, and it recomputes the height of the parent node. If the parent's node hasn't changed in height, we're done. If not, we call rebalance to rebalance the parent. And then we just do this little algorithm here. So that's it. Okay? So this, you will find that you actually don't have to write very much new code for lab B. Mostly it's just copying the code from laba.cpp and making a few strategic changes, especially after we gave you the code for rotate yesterday in lab. So there's not all that much that you actually have to write. It's a matter of figuring out exactly how to do it. So questions about any of this? Yes, Scott?
So you say if the parent node is imbalanced, rebalance the parent tree.
Mm-hmm.
And then after rebalancing,
If the parent's height. If after rebalancing the parent's height hasn't changed, you're done.
If it has changed,
Then you have to keep, you go back to the top of the, this is what I meant by iteratively check the parent node. So
Do you go up to the parent's parent?
yes,
now?
the parent's parent. Mm-hmm. So iteratively check, let's say do, iteratively check parents' nodes from the deleted node to the root. Okay. So you can break out of that, so B can break out of the loop if at some point one parent's height hasn't changed. Okay, here's the second thing that's very important. While you're doing this iteration, it says if the parent node is now imbalanced, rebalance the parent's tree. If after rebalancing the parent's height hasn't changed, you're done. Notice that it's possible that step A will find that the parent's node, that the parent's tree is balanced, but its height is different than it was before. You still have to keep going. You're only allowed to stop if the parent's balanced and its height hasn't changed. If you find in step A that the parent's tree is balanced, that is, it satisfies the AVL condition, but the parent's height has changed, you still need to go up to its parent. You're not allowed to stop. So the stopping condition in B is a dual condition. It has to be that you're both balanced, meaning you satisfy the AVL condition, and the height hasn't changed. Okay? So don't fall into that trap of saying, coming to a parent saying, oh, it's balanced, I can stop. No, you can't. You also have to make sure that its height hasn't changed. Okay? And with insert, all that changes is you iteratively check from the inserted node. That's why you don't care in rebalance whether it was a insert or a delete. You just pass the imbalanced, or the node you're checking. I shouldn't even say imbalanced. You just pass the node you're checking, which is always the parent, to either the deleted node or the inserted node, and you simply perform your checks. Okay. Other questions? Okay. When you get to 302, you will find that this is not the only algorithm that can be used to keep trees balanced. There have been a lot of research into the most efficient way to keep trees balanced, and you will be introduced to two additional types of balancing schemes, one called red-black trees and one called splay trees, that also manage to keep them roughly balanced and support order log n operations for find, delete, and insert. But we're not going to go over them in this course. They are put off to 302. Okay? Like AVL trees, you'll find that red-black trees maintain a pretty strict balance condition. You'll find that splay trees relax the balance condition, which allows the code for splay trees to be simpler and, I believe, on average more efficient. But they guarantee that if you do a sequence of n, so splay trees will guarantee that if you do a sequence of n operations, that the total time is order n log n, that is, n times log n. But they won't guarantee that an individual operation takes log n time. So you'll be introduced in 302 to what's called amortized analysis, where you'll find that as long as this is perhaps the curve for n log n, you'll find that the operations for a splay tree might go like this, where they're very efficient, and then all of a sudden there's one super inefficient operation. Boom. So a splay tree may have a couple really inefficient operations that take more than log n time, but because they have so many intervening operations that take much less time, they always stay under this n log n curve. And therefore, for any set of n operations, the average time is log n, which is a pretty cool thing that computer scientists often do, is they say, what happens if we don't require that we don't guarantee that every single operation take log n time, but we guarantee that a sequence of n operations take that much time. Okay, and sometimes you get simpler algorithms as a result, and splay trees, you will see, is an example of that. Okay, but again, we won't be covering those in this course. But we will be covering, as our last data structure, something called BTrees and their cousins, B plus trees. So binary search trees are binary. They can have, each interior node can have at most 2 children. It seems a logical thing to ask is there any reason why we restrict it to 2 children? Why can't we have multiple children? And the answer is there is no reason why we can't have multiple children. So B trees are a generalization of binary search trees that are allowed to have up to m children. So BTrees allow each node. We say a BTree, we'll say actually a BTree of order m. Allows each node to have up to m children and further requires each interior node to have the ceiling of m divided by 2 children. So there's also a lower bound on the number of children. So that's the ceiling function here. So if m is 5, you're required to have 3 children. Okay, now there's one exception, which is the root is allowed to have fewer than m divided by 2. That's the one exception. But everyone else has to have m divided by 2 children, or a minimum of m divided by 2 children if it's an interior node. Okay, and let's look at an example. So in this one, Dr. Planck came up with someone else's notes. So here we just have the keys are on top. The keys are on top, EKP, and then pointers to each of the subtrees. So the requirement is much like what you have for a binary search tree. So everything in this child has to be less than E. Everything in this child has to be between E and K. So here, everything in this node must be greater than E and less than K. Everything in this node must be greater than K and less than P. Everything in this node must be greater than P. Everything in this node less than E. So basically, you look at what the key is, and then everything in its left child must be less than it, and everything in its right child must be greater than it. So it's the same kind of condition. So for each key in a B tree, it's all keys in its so-called left subtree are less than, for each key K in a B tree, all keys in its left subtree are less than K, and all keys in its right subtree are greater than k. Now right here, you're actually not looking at a B tree. The reason I know that is that, first of all, not all the leaves are at the bottom level. So here's a leaf, and here's a leaf right here. Actually, here's two more leaves. Actually, here's three leaves. They're not all at the bottom level. And secondly, this fellow right here doesn't have enough, right here, this one, doesn't have enough children in it. So the B tree is going to actually have a few more conditions on it. So I wish I could just find a way to copy this over to here, but I can't, and I'm not going to take the time to rewrite it. But the second condition over here, okay, so the second condition is what I just wrote right here. So this is condition 2. For each key k in a B tree, all keys in its so-called left subtree are less than k, and all trees in its so-called right subtree are greater than k. So when you look at a key, it always, this would be its left and this would be its right. Okay, if you look at P, this would be its left and this would be its right. So that's why I put them in quotes. Okay, because there's multiple children, but you can kind of think of each key as having two children. Okay, if you look at Q, now for Q, this tree is like its L and this tree is like its R. Okay, it has no, in this case, left subtree. Again, this is what's called a multi-way tree. Let's go down and show you an actual B tree. Okay, so here's an actual B tree. And there, every single interior node has, each key has its own, quote, left and right trees that you can refer to. All leaf nodes are at the bottom level. Okay, so that's another condition. So all leaf nodes. 2 on other slide. 3, all leaves are at same level. Okay. Okay, what else do I want to point out about this? Okay, so this is a B tree of order 5. So right here we have a B tree. Come on. This is a B tree of order 5. Okay, so you can see that every interior node, there's only 2 of them here. We have the root and then we have 2 interior nodes. Okay, this interior node has 3 children. This interior node has 4. Okay. One thing to keep in mind is that if it's of order 4, then every interior node has a max of m minus 1 keys. So that can be confusing. You're thinking, oftentimes when students look at a B tree, they say it's of order 5, and I've said it must have a minimum of m divided by 2 children, and someone points to this node right here and says, wait a minute, no, there's only 2 children there, it's wrong. No, it has 3 children, 1, 2, 3. It has 2 keys. But it has 3 children. Okay? Now, what do you notice about the children here? Are they allowed to dip under the so-called m divided by 2 ceiling? How many keys do most of the leaves have? Keys, 2. So at the leaves, you're allowed, so the leaves may have, how many keys do you think is the maximum for a leaf? It's m minus 1. It's true for any, yes. So I really could have 2 and, wait, was that 2 or was it? Yes, actually all, so I should say all nodes. So let's change that to all nodes. Actually, let's do this. All nodes, both interior nodes and leaf nodes, may have a max of m minus 1 keys and a min of the ceiling of m divided 2 minus 1. Okay, so I also wrote up here 2 different things. I had B trees and B plus trees. The question is, what's the difference between them? The difference is that B trees store records, which are values, in interior nodes, as well as the leaves. B plus trees store only keys in interior nodes and store records in the leaves. So in a B tree, a key will appear only once. So in a B tree, a key appears only once. A key appears only in one node. In a B plus tree, the key may appear in one of the leaves with its record, and may also occur in one interior node. In practice, I'm not sure I've ever seen a B tree. I've only seen B plus trees. Okay, B plus trees are used in databases a great deal. They are, what happens is in a database, you have to have what are called indices. Let's say that you have a bunch of, the Social Security Administration is keeping records of all Americans. Okay? Well, if it wants to have fast access to Social Security records, it's going to have to use some kind of index. And what it wants in a B tree, the advantage of B trees is they are very wide because they have so many children, their depth is much less than a B tree. So a B tree, if it has n nodes, a BST, binary search tree, if it has n nodes, has roughly log 2 n depth because it has at most 2 children. But a B tree and a B plus tree with n nodes of order m has roughly, minimally, instead of log 2, m divided by 2 n depth. Because in the case of, let's get rid of, don't want this. So and let's make this clear. So with a B tree and a B plus tree, they have that at minimally m divided by 2 children. Therefore, they split the search space by m divided by 2 at each step rather than splitting it in half. So for example, if you have a B tree of order 100, it's going to split the search space 50 ways each time. So it's going to be much less, its depth or height, let's call it height, is much less for a B tree or B plus tree. And that's a huge advantage in a database. And the bigger you can make m, the bigger you make m, so as m gets bigger, so as m increases, this thing decreases, which is what you want. Well, if you're not storing records in interior nodes, you're not blowing a lot of space on records, right? If you have, let's say, 4,096 bytes, which is a common amount of memory that you would have on a disk. I'm not going to get into a lot of details here, but you have 4,096 bytes in which to store your children, and let's say your keys are 4 bytes and your records are 100 bytes. If you store the records in the interior nodes, you're only going to get about 40 keys in there, right? Does that make sense? But if you're storing just the keys, which are 4 bytes, you're not going to get 40, you're going to get roughly 500 because you're going to have another 4 bytes for your pointers. But you're going to have roughly 10 times the fan out. So that's why B+ trees are preferred in database systems. Okay? And the reason you rarely see B trees is that in memory, binary search trees tend to be much more efficient than B trees. So if you just can store everything in memory, then a binary search tree, a balanced one like an AVL tree, is going to be much more efficient than a B tree. If you have to store it in secondary storage because there's not enough storage to store everything in memory, a B+ tree is going to be much better than a B tree because it can shove far more keys into the interior nodes. Okay, so on Tuesday, we will go over the operations for a B tree. So today I just introduced them. The big question is what happens when you insert, how do you find a key, how do you delete a key? We'll go over all of that in class on Tuesday. We're never going to get to the code. The code's is too complicated and not worth looking at, but we will show you conceptually how to do it. And then next Thursday, we'll be looking at big O notation in some detail.